All right. Well, it's starting to get warm now. Get nice out again. Days are staying a little bit longer. So maybe you're outside walking in the evening now, and maybe sometimes you will see your shadow again. Unless it's a cloudy day, maybe you won't see your shadow then. This problem talks about how you need to be aware of your shadow. Beware your shadow. Have you ever watched Peter Pan? That shadow in Peter Pan's kind of a little creepy. Kind of does what it wants to, and it even detaches itself from you. So be a little afraid of your shadow. This problem is going to kind of tell us why. But we'll get back to that in a moment. A 5 foot tall person is approaching an 18-foot tall street light. Okay. Our question is this: how fast is the tip of their shadow moving? How fast is the tip of their shadow moving when they are 10 feet from the street light? And the person is moving at a constant rate of 3 feet per second. Okay. So we want to know how fast the tip of their shadow is moving at when they're 10 feet away from the street light, and they're moving at a constant rate. So to kind of understand this thing, let's draw a picture. So here's the situation here. I have a street light over here, 18 feet tall. And I have my 5 foot tall person, kind of a short person there, walking along, and they're heading towards the streetlight. They're going this way, towards the streetlight. Currently, they're 10 feet away, but as they move to the streetlight, that distance changes. So I have to label that as a variable, and I call that variable x. I also need to know how fast the tip of the shadow is moving at. Shadow tip's right here. Because understand what happens is street light is sending light beams out, and your shadow is created by your body blocking the light from getting to the part of the road behind you as you walk towards that street light. Okay, and so your tip of the shadow is going to be down there. That's going to be the top of your head. And that's also going to be moving as you start walking towards the street light. As you're walking towards the street light, you look behind you, your shadow moves. Your shadow is moving along with you. Creepy little thing. So here we have our information that we need. Then let's kind of write down some of the stuff that we know. We want to find dy dt. We know that dx dt is negative 3 feet per second. We know it's negative 3 because x is getting smaller. And we also know that at a particular point in time, x is equal to 10. So just like in the previous problems, we need to look for a relationship between x and y. We need to find a relationship between x and y, right, and then differentiate that relationship implicitly with respect to time so that we can eventually solve for dy dt. So here's what we know. Well, how do we find how x and y are related? Well, I marked another distance on here in purple. And I'm going to label that distance, since the red distance is x and the blue distance is y. That little purple distance will be y minus x. And so then we got to find some way to get x and y related. And the idea is to realize that this little triangle here and this big triangle here are in fact similar triangles. How do we know they're similar? Well, they both have a right angle, and they both share this angle. And we know that the three angles in a triangle add to 180, so that means their other two angles here have to be the same as well. And if you have triangles that have all three angles being the same, then they're similar. They're similar triangles. And one of your results from geometry is that if you have similar triangles, then ratios of corresponding sides are equal. Ratios of corresponding sides are equal. In other words, the sides are in a constant proportion in that triangle. That was one of the results you used to find, originally to find the trig functions. Once you had a particular angle, no matter what triangle you looked in, tangent of 30 degrees is always the same thing, 1 over the square root of 3. So with that in mind, we can write down a relationship. Taking the purple length there, y minus x, over the height of the person, right? Those two sides of that little triangle, the base and the height, that has to be the same as taking the big length y divided by the big height, 18. And now we have an equation relating x and y. Now we could go ahead right now and differentiate this equation implicitly. By the way, you could have done this other ways. You could have did 5 over y minus x equals 18 over y. There's some other variety of things that you could have done. You could have even done ratios of the sides. Y minus x over y equals 5 over 18. Or you could have done it like that. There's different ways to set that equation up. So we could do implicit differentiation right now, but it's a whole lot nicer if we clean the equation up first. Put it in a different format. So here I can cross multiply. I have a fraction equal to a fraction. So I cross multiply. Cross multiply. And then I have 18y minus 18x equals 5y. So why don't we get the y's on the same side and the x's onto the other side? Just bear with me for just a moment. So bring the 5y over, it gives me 13y. Move the 18x over to the other side, it gives me 18x. Now this equation is in a really nice format, and it's really easy to do implicit differentiation now, because derivative of 13y is just going to be 13 dy dt. Derivative of 18x is just going to be 18 dx dt. And so that dy dt can be written as 18/13 dx dt. So notice here an important idea that is different than some of our previous examples, and that is that 10 feet that we're away from the street light doesn't matter. Dy dt is always going to be 8/13 of dx dt. And so we know that dx dt was a -3, so we can plug that in. And we get that the tip of the shadow is moving at -4.15 feet per second. It's negative because it's moving toward the street light, and that distance is dropping. So at the very beginning we said beware your shadow, and here is why. No matter how fast you go, if you're going towards a street light, the shadow moves faster than you do. Okay, say that again. The shadow moves faster. In this scenario, it's 18/13 as fast as you are. So creepy shadow is faster than you are if you're going towards a street light. Now, a bit of good news. If you actually make it to the street light, the shadow's gone. If you actually make it to the street light, the shadow's gone. Because the reason the shadow is moving faster is as you get closer to the street light, the shadow is shrinking. So the shadow's actually moving the same rate as you are, but it's also shrinking, in this case, at a rate of 1.15 feet per second. It's getting smaller as we continue to go towards that street light. Okay, so here's just one more example here of a related rate problem. This one involved, again, a triangle as well, but this time we had to do proportions instead to get the relationship. Till next time.